So, okay, a more regarded by many experiments, many study, a good model for visible light and near-infrared light is radiative transport equation. Okay, radiative transport equation. Okay, so let me tell you what it is. It's very heavy, probably. But how should I say? Okay, as I promised, it's heavy because it's one equation worth 1,000 words. So, but most importantly, I'll give you a very nice interpretation. But this equation, let me tell you what are the most important things in this equation. These are the optical property. This is the transport coefficient, which is actually composed the sum of absorption coefficient and scattering coefficient. The scattering coefficient is here. So this absorption coefficient really tells you like the blood volume. Depending on the blood volume, this can vary a lot. Although in using other modality, you don't see much differences in this, but if using light in this spectrum, they will tell big difference from this measurement. And so we are trying to, this is a way of describing the light propagate, and what we're interested in is to recover these two coefficients, okay? So let's give a more physical interpretation why this is a good model. Okay, this is again the equation. So the terms here, they are, for mathematician, all these terms are quite simple. Okay, these, let me tell you what they are. Okay, first of all, think of a photon. Okay, the photon. So it's a photon at this position also has a direction to travel, right? It asks this location at this direction to go. Okay, when you go through the medium, if you have high energy, high frequency, it's like X-ray. It's very interesting. The photon comes into here, and if you come in this direction, it just go all the way to this end in that direction in a straight line fashion. It just intensity decays. So that's the X-ray. Okay, because you're using high energy, high frequency, the mathematical model can be that simple. But with less energy, a little bit higher, lower frequency, the particle will be, its path will be affected by the underlying medium. So it's want to go straight, but then it's scattered and zigzag way. And this is basically saying when you go through this, the photon in that direction is absorbed, but also scattered to other directions. So you have fewer photon in this direction. Okay, that's where this telling you. But on the other hand, the photon traveling in the other direction will again scatter back into your direction. So this is telling you the photon in different directions, how do they interact with each other. But anyway, so this is, they like to go through a straight line, but then different photon in different directions, they will interact. That's basically what it is. And in particular, this is what physicists and engineers are very good at. They can know in medium, they can tell you very well what the F is. So how the interaction between the photons in different directions. They know this function very well. So the whole mystery in this equation is we want to know the mu t and mu s, and mu t minus mu s is the real things we want to know. We want to know the absorption coefficient. Okay, so the thing is, how do we, we know light propagate follows this mathematical model equation. The question is, we know more quantitatively, how do we do it? We want to solve it, right? We need a forward model to tell you what my input is here and what is my output. So my input would be Q, okay? I want to predict the phi only at the boundary. And then from that, I want to recover the mu t and mu s inside the body. Okay, that's the whole process. Well, then the thing is you have to solve this RTE. How do you solve it? Well, it turns out this equation, mathematically speaking, if you speak very abstractly, some of my colleagues doing pure mathematician, they usually study in a more abstract, more qualitative way. And this equation is very simple. It's a linear equation, It behaves very nicely, has a unique solution. Don't worry, it always has solution. But on the other hand, it doesn't have an analytical formula because the problem is, as I said, many problems are so complicated, you cannot write an explicit formula out. But when you do imaging, you always measure the data in digital data. Then the question is, you want more quantitative expression or solution to this equation. Then you have to use computers. Okay, that's again how computers use mathematics to solve real-world problem. So the first thing is, given such an equation, how do you ask computer to solve it? Okay. Well, there are 3 steps, the major steps. The one thing is, the original problem in the variables R, in the physical location and angle S, they are all in continuous spectrum. There are infinite many R and S. So the first thing the computer can only deal with finite number of things, although it can be 10 to the 24th, 10 to the 30th, but only finite. You cannot infinite. So you have to reduce the continuous problem to a finite dimensional problem. We call that discretization. Then you can design an efficient algorithm to solve that discrete problem. And the third thing is you have to code it up in computer and really use a computer to solve it when you have real data and so on and so forth. Okay, so let me go quickly. So this is typical discretization. Our angle is in a sphere, right? All directions in R3. So that means the angle live in a unit sphere. You have to discretize this, and this is typical discretization. Well, the light is okay. Is here, so you put all this grid on this, and those nodal points is where you will compute. Okay, you will only compute using only those discrete directions rather than every direction on the sphere. Then your equation, especially the integral term, will be discretized as a large summation term. Okay, but you have many ways of doing this. But if you do right, well, our way is right in a sense. Mathematically, you know why it's right and not. You're not just saying after using computer to show, because you can only run 1 or 2 examples. But by doing analysis, you will see why this is right because of these properties. Okay, this is mathematical analysis, and you're doing the right things to discretize it into a finite dimensional problem. And then also you have to do spatial discretization. Okay, that's also you have to learn. That's what I said. Mathematics help. Although I don't know exactly the solution is 100, 1,000, 1.1, but I can imagine how the solution behaves. That's why when you do discretization, you want this discretization is faithful, is really relevant to that type of behavior. That's where really the mathematics helps. You know the solution not to the digits, but you know how it behaves. That's very useful. And then still, after you have the right discretization, as I said, it's still a huge problem because you have 3 dimensions in space, 2 dimensions in the angular. Okay, the sphere is a 2 dimension. So if I count all the number of degree of freedom, is the typical things. You want to say 100 grid in each direction in space, 200 angular direction, then the total number of degree of freedom is 2 times 10 to the 8th. Forget about 2, just 10 to the 8th. Direct solving this linear system, okay, which means you're doing Gaussian elimination. If you learn how to solve 2x2 systems, subtract one from the other and getting a triangular system and solve it back, it will require, I think, 10 to the 8th or 9th gigabyte memory. I don't think anybody has that computer. And also, if you want to store the inverse of the matrix, okay? And also, if you want to calculate all elements of this inverse matrix, it will take 2 gigahertz memory, hundreds of years. No one can wait 100 years for such one simulation. Okay, so then you cannot do this, then you have to find better ways of doing that. The most important thing maybe for this, just quickly summarize, you cannot invert a matrix. You cannot do that. You can only use matrix multiply a vector to approximate the inverse of matrix. okay? Because the matrix itself is sparse, but the inverse matrix is not sparse. So you cannot do that. You just have to do, basically, you want to use multiplication to do division. So something like that, but it's more complicated. It's a matrix.